Here is problem number 17 from chapter 5. In it, a customer sits in an amusement park ride in which the compartment is to be pulled downward in the negative direction of a y-axis with an acceleration of magnitude 1.24 g, with g equaling 9.8 meters per second squared. Just a quick note, some students get kind of confused with these things with the g next to it. All that means is that you take the number in front of the g and multiply it by 9.8. And that is the entirety of the acceleration. So a 0.567 gram coin rests on the customer's knee. Once the motion begins, and in unit vector notation, what's the coin's acceleration relative to the ground, relative to the customer? How long does the coin take to reach the compartment ceiling, 2.2 meters above the knee? And then in unit vector notation, what are the actual force on the coin and the apparent force according to the customer's measurement of the coin acceleration? So you might notice I haven't drawn a picture yet, which I typically do. And the reason why is because I have this friend right here to illustrate what's going to happen. I think sometimes understanding what's happening is the trickiest part. So this little dude is going to be going on this amusement park ride. It's kind of like drop zone, like he's dropping straight down. But he puts a coin on his knee. So normally, let's assume that this is the upward direction, this is the downward direction, and that gravity is pulling us down in this downward direction. Normally, if you drop a coin, it will just accelerate in the downward direction. So if you put a coin on somebody's knee, the coin will still want to accelerate in the downward direction, 9.8 meters per second squared. But our dude here is accelerating downwards faster than that. Essentially, the ride is pulling him down faster. And so here's what's going to happen. He is going to be moving and the coin is going to be also falling, but from this guy's point of view, it looks like the coin is going up. So let's see that instant replay one more time. So he's going down, the coin is also going down, but since he is going down faster, 1.24 times g, and this is only going at g, to him, it looks as though that coin is just rising up above him. So that's the premise of the question. Now let's solve. He can just hang out right here and watch what we're doing. So first of all, our first part is saying what is the acceleration relative of the coin relative to the ground. And so as rest, the acceleration relative to the ground is just negative 9.8 meters per second squared, because it's just gravity. There's nothing else that's actually affecting the coin. But I do believe that we are supposed to answer this in unit vector notation. Is that true? Yep, unit vector notation. And so that is in the j direction. And so I would say my acceleration equals negative 9.8 meters per second squared j hat. So we are done with part A. Now part B, we want to know what's the acceleration relative to the customer. Now this is decidedly more tricky. If you have not yet learned about relative motion, now is the time. So here's the trick. If I have an acceleration of object A with respect to object C, then that is going to always equal the acceleration of object A with respect to B plus the acceleration of B with respect to C. Essentially, you start the first term here and at the beginning. The last term is here and at the end. And then the middle terms must match each other. As long as you do that, then that is how we can solve for relative motion. So let's do that for our current situation. And so I'm going to use C to mean coin, G to mean ground, and it would be really nice if customer started with a letter other than C, but customer obviously starts with C. So I'm going to use P for person, just so that we can distinguish between these three when we're talking about our relative motion. And so what I want to solve for is the coin's acceleration relative to the customer. So the acceleration, oh, sorry, little guy, you're going to have to move. So the acceleration of the coin with respect to the person is what we want to solve for. We already know that the acceleration of the coin with respect to the ground is negative g being a positive 9.8, and so I'll just put the negative indicating that we're going downward. And we also know that the acceleration of the person with respect to the ground is negative 1.24 g. So this is what we want to know for part B. This is what we already do know. And both of these just going downward, hence the negative. So I'm just going to set up a relationship like this for my acceleration of the coin with respect to the person, because that's what we want to know. Coin's acceleration relative to the customer. So acceleration of coin relative to the person equals A, acceleration of the coin. And you notice I don't have ground in here. So that's going to be kind of my middle term here. So acceleration of the coin relative to the ground plus, and I'll just follow the pattern I see here, acceleration of the ground relative to the person. So I know that this is true. I also notice that I don't have acceleration of ground with respect to person. I have acceleration of person with respect to ground. But the way that this works is that if you want to know the acceleration of the reverse, that's just going to be the negative of whatever you have. And so the acceleration of the ground with respect to the person is just going to be positive 1.24 g. So now that I know all this information, I can just plug it in here and find out what this acceleration is going to be. So I have acceleration of the coin with respect to the person equals acceleration of the coin with respect to the ground, which is negative g, and then plus acceleration of the ground with respect to the person, which is 1.24 g. And so I find out that the acceleration of the coin with respect to the person is just 0.24 g. And if I multiply 0.24 times g, I will end up with 2.35 meters per second squared. And of course, we still want that in unit vector notation. And just as we suspected, acceleration of our coin with respect to the guy is going to be positive because he sees it moving up with respect to the ground, or rather with respect to himself. And so our answer, acceleration of the coin relative to the person, is going to be 2.35 meters per second squared j hat. And so we have solved for part B. And then if I want to know how long does a coin take to reach the compartment ceiling, 2.2 meters above the knee, then we are really just dealing with this coin going up at this acceleration because our compartment also has our acceleration of 1.24 g in the downward direction. What that means is that I can use this acceleration to solve for the time that it's going to take. And so here we are over here. You can look at us right here, guy. And so for this, I know that x equals x naught plus v naught t plus 1/2 at squared. And I'll be using these all in the y direction. And so we're going to end up at 2.20 meters above. We started at 0, so that we know the time. Our initial velocity is 0 because we just started from rest on the customer's knee. But then our acceleration is this upward acceleration to get to the top of our compartment ceiling. So 1/2 times 2.35 times t squared. And so this is what we need to solve. We find out that our time via our calculator, we'll find out that it's 1.37 seconds. And next on to part D and E, what is the actual force from the coin and the apparent force according to the customer's measure of the coin's acceleration? So for this, if I want to know force, I know that force equals mass times acceleration. So my actual force would use the acceleration of negative 9.8 meters per second squared. Of course, don't forget that we are given our mass in grams. And so my mass, you'd want to use it in kilograms. And so we would have 0.000567 times our actual acceleration. And so for this, we would end up with negative 0.00556 newtons. And so, of course, in unit vector notation, my force will be, I'll put it in scientific notation as well, negative 5.56 times 10 to negative 3 newtons j hat. And lastly, for part E, the apparent force would be using our apparent acceleration. And so again, F equals ma, always write the equation you're starting with. This will equal 0.000567 times 2.35. And so our force in unit vector notation will equal 1.33 times 10 to the negative 3 newtons j hat. And we're done. See you later, little guy.